Good morning, everyone. Um, Welcome. Today I'm going to be talking about registerization, which is essentially how we figure out what values are going to live in registers. We're not going to pick which registers yet, that's later, that's register allocation, but we're going to talk about which values from a Nock computation live in registers. We talked about before, nouns are tree shaped, so we need to pick out nodes in the tree or leaves of the tree if we want atoms to live in registers and say this piece of the tree is going to live in a register. What I'm going to be showing you today is it's not a raw and fresh brainwave, but probably medium rare to rare. Uh, I had a inspiration late yesterday about how to combine destination-driven code generation and registerization and throw out the mutable noun stuff we talked about in a previous stream. So we'll just talk a little bit about this first. There's a paper called Destination-Driven Code Generation that I have up here. I talked about this technique as applied to Nock a little bit before, but we're going to actually pull up the paper here. So destination-driven code generation was written by Kent Dybvig, a couple other people, as the style of code generation used in Shea Scheme, which is a very fast scheme compiler that generates very fast scheme code. And the core idea is in this function signature right here. So the code generation function takes an expression. In this case, it's a C expression. The paper's written from the perspective of compiling C for VAX, actually. But generalizes quite nicely to a lot of different things. Takes an expression in the top level programming language, takes that expression's environment. In Nock, we don't have a fixed environment. Our entire environment comes in as a dynamic parameter. We call it the subject, so we'll skip that parameter. It takes a data destination. This is essentially telling us where do we put our result. So code generation is parameterized on where are we going to put our result, and it takes a control destination. The control destination is a label or a pair of labels. Although at some point we're going to pass in the special label. When we start, we're going to pass in the special label return. So the top level expression is going to have destination return, meaning that this expression is in tail position. What we're going to do with this is we're actually going to, for Nock, we're actually going to traverse this function in this style sort of backwards over the Nock expression tree. We are going to visit nodes generally before their children, but we're going to visit, because in Nock data flow dependencies generally go from more left children earlier in the improper list of sub-expressions to children further right, further down that list. We're actually going to traverse kind of in reverse along there and bring the data flow. So we'll be traversing in the reverse order of the data flow. So from data flows through the expressions and then up to the enclosing expression. So we'll start with the enclosing expression and flow backwards. So what does that look like? If we take a look at Nock again, if we look at, say, Nock 7, the result of Nock 7 is the result of whatever expression fits in metavariable C there, but the result of but that is dependent on a subject that is the result of metavariable B. So our data flow is the top of the expression comes straight from the result of metavariable C, but that expects data from metavariable B, which expects the subject of the expression. So our data flow, again, kind of flows right to left as you read the expression tree. So the inspiration here is that if we generate in this sort of reverse data flow order, we can generate labels for code blocks that we generate and return those from our recursive calls to the code generation function. We can generate expectations or uses of the data formatted as a tree that should match the result value of some noun and say what locations in the tree are actually used with freshly generated symbols for SSA values. And then we can pass this tree in as a data destination and format our data destination in that way in order to say, please place your results into these SSA registers. Then when we get to the very top level, where we expect the subject for the whole formula, we have a result that tells us where to put the subject. So this allows us to discover not just uses within the formula for an arm. Arms in Hoon very closely correspond to the compilation units in New Mars. So it's not just internally to an arm. Within its formula, we can discover uses and put them in registers, but we can actually say that this arm uses these parts of its subject and expects them in registers in this order. So like I mentioned, this is very raw, so I don't have a completed code to walk through. And instead, I'm going to try to work on this a little bit live and just kind of show you guys what I'm on about. So this is a, on the left here, we have a rewrite of gene.hoon where we have the types for the code generator. So we still have the same label type, the same internal label type, the same control flow destination, but our data flow destination now looks like this. It's either the result of an arm, and if the data flow destination is the result of an arm, then the control flow destination should be return. Wherever we depend on that, we'll put an assertion. It can be the result of a hint, and the reason we'll mark this is to generate an instruction that later, when we try to do dead code elimination, will prevent us from eliminating dynamic hints that might crash, because that would be semantically incorrect, as the commentary on the Nock specification points out. Or it can be this sans type, which is a map from the shape of a noun to some SSA register. So this is a little bit similar to SOC, as we talked about in the stream on subject knowledge analysis, in that we're sort of describing the shape of a noun, but rather than describing what we know about the noun, we're describing symbolic names that we'll want to attach to the noun. So it's in the default case, it just means we don't have names for any part of this noun. In this case, it means at this point in the noun, we're going to give it this name that's denoted by just an atom. And at this, this means we're going to have multiple names described by cells. So the children of this could be more cell splits, or they could be SSA registers, or dis for disregard. So this is the main structure for our data flow destinations. And so what this will allow us to do is, for instance, if we look at the autocons case, let's fix this up just a little bit. I just sort of restructured the outer state of the core here so that we can keep track of a fresh SSA variable that hasn't been used in our code yet, and continue to generate more and more SSA variables without generating conflicts. So let's make an arm that will just give us a fresh SSA variable, and the arm will give us back a pair of an atom and something that is the same type as the state, so that we can put this back in place of the state, and it's just going to return and put back the state with its increment. So this will excuse me. This will allow us to generate fresh names. So now let's start our pattern match here. So we're going to pattern match on the current formula that we're working on. We call fate up here. It's initialized to the formula from the label we were passed in. And we have this bomb helper down here that will generate a crash for us, give it a label that we can return. But the entire thing, this is if we try to evaluate an invalid Nock formula, would just generate a crash instead. So this is the very first case in the Nock spec. If we have a formula that's a pair and the head is also a pair, then we're going to run each formula individually and generate a cons. But remember, we're going to work backwards. So we're going to first write the code to put together the result of the cons, and this will give us back data destinations and control flow destinations for, it'll give us back data destinations for both of these and a control flow destination for the tail. The control flow destination of the head will be to jump to the evaluation of the tail. So first we want to know what's our control flow destination. So we'll match on here. If it's bab, which means that our control flow destination is a branch, we need to match on a result and branch on it. Well, this actually should just crash because branch should get a 0 or a 1, and a pair is not even an atom, let alone a 0, 1. So we know that if we generate a cons as the test condition for, as the test result for a branch, then that's just going to crash. That's not even valid. If the destination is return, then we'll first verify that the value destination is result, and if it isn't, again, we'll crash. So given that assertion, we actually need to generate a label for the head of the pair, a symbol for the head of the pair's data flow value, and update the state. We also need a symbol for the tail, update the state. And sorry, I've just got to look at the types here, because what we're going to try to do now is recursively call not this whole line generation function, but just this internal function. So what we actually want is the inner state and return that. That's actually, no, that's still the wrong spot, because we just care about this. We actually don't want to return all of this, because this is intended to be passed down. So with that in place, we can say that the next thing we're going to want to do is generate a cons instruction, which let's look over here at the type we're going to put into box and our label will be the return cons. The here function down here is just taking some discriminating local label and then generating a label that has our subject, our knowledge of our subject, our outer formula, the access into the outer formula where we are right now, and the and putting that together with what we pass into it. So we're just going to name this basic block that way, and then we're going to need we're going to need one more, because what we're going to do is put in a cons instruction there, and then so this generates an exit point. So remember that this is what happens when we are in tail position. So this is generating an exit point where, because we'll always return in a single register, we're generating the instruction to actually take the results in the head and the tail and explicitly allocate memory for a cons cell and put the result of that allocation in this new SSA variable, and then return that new SSA variable. So we've done that first. So this is the end of the data flow line right here. So we're going to cons up the result, and we're going to return it. And then we're going to say the control flow for the tail and the data flow for the tail and then the local state come from recurring on. Now we're going to talk about the tail. So this is going to be the tail of our current formula. The new axis is going to be axis 3 underneath. So peg just composes axes. So you have the current axis and you have the axis underneath that, and peg just composes those. Oh, we need to say where we're sticking this. Error is just a direct jump to the code we generated above, and veil is just, let's remember what words we used up here. Stall. So put your whole result in this register, please, because we're going to cons it up. So let's go ahead and make this a little bit more call form. And so this will put the code for our tail in. And now we can just go straight along to generate code for our head. Control flow for the head. And this will look very similar, except we're going to take the head, we're going to take axis, compose axis 2. We're going to directly jump to the control flow label returned by the tail. And our value destination is the head. All right, so now all we have to do is make these two values match up so we can return them. We're going to delegate that out to a helper, but in general this is going to look like running down the tree together, taking the more pessimistic, taking the deeper one from each side and generating consing instructions if something expects something higher up, and if something disregards on the other uses, then of course we'll just put the use in both. If there are uses at the same place, then we'll just generate explicit move instructions to copy from one use to the other and return the source of the move as the data destination. So we'll just generate copies there. So we're just going to assume that we have this, the control flow label for that, and the value for the whole subject from merge the head and the tail value things. We're going, again, we'll put this down here as a helper and make it a to-do for later. So hopefully this gives an idea of how this works. So to go back over this real quick, and let's just put our return together real quick, we can actually just make this part's return value our whole return value, because whatever value expectation of the subject it returns will be the value expectation of the subject for our whole thing. We can do other cases for this. We could do the jump case, in which case instead of generating these fresh this way, what we'll do is we'll generate code to split the incoming SSA value and or split the incoming SSA map and hand off the left half of it as a destination to the head and the right half as a destination to the tail, unless it expects the whole thing in a register, in which case we're just going to put together this cons code again, except not allocating a fresh register for the result. We'll just use the expected register and generate fresh registers for the head and the tail as destinations and generate an explicit cons. So there's some impedance matching code, and what this means is we're trying our best to make data flow through registers. And allocations result from a mismatch in expectations between how something is generated and how it's expected to be used. As will, we'd see in other cases, sometimes you need to go the other way, and this will happen in merge, where something might come in a cell and we'll actually need to generate. So here's the cons instruction, checked head instruction, and then there's an unchecked head instruction which we won't generate in this pass. But if you're asking where does subject knowledge analysis come in, the plan is actually to do subject knowledge analysis on the output of this pass and flow the subject knowledge through the SSA registers. And then if you know safely a value in an SSA register is a cell, and then you're going to take ahead of it, you can actually turn that into HUD. And the difference at machine code generation time will be essentially whether or not you check the tag bit for a cell and branch to a crash. Because if you already know for sure it's a cell, then you don't need to check that tag bit, and we can keep a branch out of our code and just directly go through a pointer chase. So I'll stop there for now. Hopefully that gives you a taste of what we're trying to do in terms of registerization, and